I'm giving a talk, but also, yeah, also the previous time I think I gave a talk on Zoom, so hopefully at some point in the near future I can also visit the in person. But for the time being, I'm very happy to give a talk about this topic about the cutting rules for the in correlators and the cosmological collider. So by the way, can you actually also see my like a castle as well?
Yes.
Yeah, that's great. Okay. And then, yeah, so this topic is a bit maybe technical, but I'll try to, because this paper is actually about a technical detail. So I will try to explain, I will try to, explain actually the technical details about, those kind of engineering correlators. So hopefully you can, kind of understand it. Also, yeah, maybe before starting my talk, so I have an office mate, and then maybe he comes into the office at some point. I'm sorry if there is some like an intermittent interruption, something. Okay, and then my name is Yohei Ema. I now started working as a postdoc at CERN, and then this talk is going to be based on this paper, evaluation with Kyohei Makeda. So, and then I also want to say that, if you have any questions, then please just ask me. Like, even though I can see you guys on Zoom in a small screen, it's better if, you can also, ask me questions if, something is not clear to you, or if you want to understand more, then, because then I can see your reactions, and also, I can see, which part I should make it more clear, and so on and so forth. So, please just, don't hesitate to interrupt me at any point in the talk. Okay, so that will be said. So this is outline of my talk. So the first part is the introduction. So today I'm going to talk about the cosmological correlators. So I want to first motivate you, like why I want to think about the cosmological correlators, and in particular the cosmological collider physics. So I will explain what are these, and also I will explain why I want to care about those kind of quantities. So that is the motivation part, the introduction. And after that, I'm going to discuss the cutting rules for the equal time in correlator. So this is actually the main part of my talk. And then after that, so this cutting rule, so this is a general cutting rule that applies to the equal time in correlators, and cosmological correlators are one of them, but you can also apply even beyond the context of the cosmological correlator. So this part is quite general, but as one application of such kind of cutting rule, I will discuss an application of this cutting rule to the so-called non-local cosmological collider signal. So I will also explain what is the EE correlators, what is the non-local cosmological correlators during the talk, so don't worry if you don't understand it. But so this section 3 is more about application of this cutting rule, and then I will summarize my talk. So this is it. This is the outline of my talk. Okay, so let me start. So the introduction. So today I'm going to talk about the cosmological correlators, and those cosmological correlators are generated, so I'm going to mainly talk about the primordial cosmological correlators, and those are generated during the impression in the early universe. So I will briefly remind you what is the cosmic impression in this slide. So we kind of now believe that, there exists an exponentially expanding epoch in the early universe, and then this epoch is called, cosmic impression. And this impression is, in the simplest case, driven by almost constant inflaton potential. So the picture is like this. So you have this inflaton field, and then you have this inflaton potential, and then you have, let's say, this kind of shape. And then let's say that inflaton has some flat part of the potential, and then inflaton is slowly lowering this flat part of the potential. So in this case, the kinetic energy of the inflaton is small compared to the potential energy of the inflaton, so that the energy density is divided by the potential, which is almost constant. So this is quite similar to just a positive cosmological constant. So if you solve the Friedmann equation, the Hubble parameter, which is the time derivative of the scalar factor divided by the scalar factor itself, is controlled by the inflaton potential, something like this. And so Hubble parameter means that your background, your metric is dependent on time, so it is actually expanding, exponentially expanding. And then if the background is dependent on time, then in general, you have some particle production. So because of this Hubble parameter, particle production happens, and usually the rate is going to be given by like exponential factor, something like this. So this m is the mass of the particle you want to produce, and then this h is coming in the denominator. So if you have the mass which is smaller than of the Hubble parameter, you can actually produce those kind of particles sort of efficiently by this Hubble parameter. And I think the most important example of those kind of particle production is actually the so-called curvature perturbations. So those curvature perturbations are created by the Hubble parameter during the inflation. So, and then what is nice about those kind of curvature perturbations is that you can actually see what kind of curvature perturbations are generated during the inflation by looking at, for instance, the CMB anisotropy and also the large scale structure of the universe. Okay, so this is the temperature map of the CMB. So, this hot region and cold regions are corresponding to the hot regions and the cold regions, respectively. And also, those are the structure of the galaxies. So on average, we know that the universe is really homogeneous and isotropic. So zero sort of approximation is just that. But if you look at the details, then there are actually fluctuations. So and then if you start from completely homogeneous and isotropic initial conditions, then you don't have those kind of fluctuations. You don't have those kind of small scale structures. So that means that those fluctuations those kind of patterns must be coming from some initial fluctuations, and then those are actually generated during inflation. So the initial condition of those kind of fluctuations are actually provided by the curvature perturbations or fluctuations are produced during inflation, which we usually call the cosmological correlators. And those cosmological correlators are evaluated at the end of the inflation. So what we think in practice is we think about the correlators of the scalar field, for instance, like this. So let's say that this is the inflaton. So this is related to the curvature perturbation by some simple scaling factor. So these correlators are generated during the inflation, evaluated at the end of the inflation. And by looking at those kind of patterns and by evolving those kind of initial conditions according to the history of the universe, you can actually get those kind of patterns. So in other words, by looking at these patterns, you can actually get information about these cosmological correlators. And that is quite interesting because those cosmological correlators are generated during the inflation because of the Hubble parameter. So that means that it encodes the information about the energy density or the Hubble parameter during the inflation. And also the change, time dependence of this Hubble parameter also affects the a spectrum of this correlator. So the derivative of the inflaton potential can also affect these correlators. And also, more interestingly, if the inflaton couples to other particles, if there exist some other particles that are coupling to the inflaton particles, then you can also see the patterns that are generated by those couplings to the other particles, and especially particle production of those additional particles, and these are cosmological correlators, and that is actually the so-called cosmological correlator signals. Okay. So in the second half of my talk, I'm going to discuss the cosmological collider physics. So I want to briefly explain what is the cosmological collider physics and what is the idea behind it. Okay, so the cosmological collider signals are aiming at detecting the particle production in the cosmological correlators. So let's say that you have this cosmological correlators, and that is given diagrammatically by this. So this red line is corresponding to the end of the inflation. So this is the future time slice. And then, so all those fields are evaluated, as I said, at the end of the inflation. So, those fields are, living here and here, those kind of endpoints. And then let's say that, those fields are connected to some operators in bulk by just, those kind of 2 points. So this thick line is corresponding to just a collection of the propagators. So if you have 2 fields here, then this is actually just the 2 propagators. But I just collect everything. Instead of writing many propagators here, I just collect them as just a one thick line here. So this is the particle boundary propagator. And then so this blob is corresponding to something that is happening during the inflation, and especially if you have the particle production. If you have some other particles that are produced during the inflation, you can have some such kind of particle propagating in between these 2 points. And then they say that the scalar sum of this momentum as KL and KR, and the vector sum of this momentum as KS. Okay. Then the cosmological collider signals in practice is encoded in this kind of dependence of the cosmological correlators on the external momentum. So here nu is given by this expression. So roughly speaking, it is given by the mass divided by the Hubble times the imaginary parameter I. And what is important here is that so this nu is in general non-integer because m doesn't have to be related to the Hubble parameter. Okay, and if this nu is non-integer, that means that this is non-analytic in terms of the momentum, because for instance you can have 1/2 or something, and that means that you have the square root. That means that you have the branch cut, right? So this kind of dependence is non-analytic in momentum, and that kind of signal is called the cosmological correlator signals. And if it depends on the vector sum of the momentum, then that is called the non-local cosmological correlator signals. And if it depends only on the scalar sum, then that is called the local signals. The reason why this is as a result of the particle production, not from some other higher dimension operators, is because the higher dimension operators, which people also sometimes refer to as the background signals in the context of the cosmological correlator physics, these are always analytic in momentum. And I think to understand this point, it is easier to just think about an example. So let's say that you have the Lagrangian, which is just given by this kind of high dimension operator. And if you have so this n should be, of course, integer. And if you go to the Fourier space, and this is roughly speaking given by this k2 to n times phi 2 to n. But then this n, as I said, should be integer. So that means that this dependence on the momentum is analytic because this is just polynomial, right? So in general, the local operators, those kind of higher dimension operators, cannot generate any non-analytic dependence on the momentum. So if you see these kind of signatures that is non-analytic in momentum, you can say that those are not coming from the higher dimension operators, which means that those should be coming from some particles that are produced in the universe and propagating and so forth. So that is the basic idea of the cosmological correlator physics. So it's interesting, given the theory, given the couplings, that you want to actually compute those kind of cosmological correlator signals sometimes. But then there is a complication in the practical computation. Maybe I will also explain a bit more about this in the later part of my talk. But so in general, those kind of computation of the diagrams are really complicated in the context of the cosmological correlators. I think mainly because there is no time translation invariance. So in the early inverse during inflation, the inverse is expanding. So the background explicitly depends on the time. That means that you cannot perform the Fourier transform with respect to the time. So you actually have to. So for instance, here and here, you have the time variables, and you actually have to perform the integration over the time. And sometimes the function that you get is complicated, and you have to integrate those kind of complicated functions. So that kind of calculations are quite involved in general. But then, so this is actually part of the motivation why I want to think about the cutting rules for the equal time inequalitors, because cutting rule for the inequalitors helps in simplifying the calculation in certain cases. And actually, it allows us to factorize the time integral. So I will explain this point more detail later. But the main point is that, so these kind of signals are interesting, but sometimes it is very difficult to compute. So the general question is there any way of simplifying the computations? And then the cutting rule helps in certain cases. So that's the motivation why I want to think about the cutting rules for the inequalitors. And so this is actually sort of the summary slide of my talk. So the goal of my talk is going to be to understand what I'm saying in this slide. So if you don't understand details about this kind of slide for the moment, then don't worry, I will actually explain in detail about those slides, this kind of slide later. But I want to just show you where I'm going in the end. So that is the purpose of this slide. So our claim is that, our main claim in our paper is that we actually can derive a general cutting rule for the equal time inequalitors, including the cosmological correlators. And that is diagrammatically given by this. So as I said, we have this kind of diagram. So all the fields are sitting at the boundary here, and that could be connected to the bulk fields by those kind of collection of the propagators. But then if we consider this kind of diagram, in general, that is given by cutting this part, and this part. And here, as I said, this thick line is corresponding to the correction of the propagators. So if you have two fields, then it is actually just an abbreviation of this collection of two propagators. And this blue color is corresponding to the average of the Wightman function. So this is just given by the Wightman function. So the important point is that there is no theta, time altering theta in this expression. So that is very important. And those arrows are representing the causal flow, how the causality flows, or how the time flows. And in particular, this function is having only one arrow that is outgoing, and all the other arrows are incoming. And this function is called the Fourier retarded function, which is a generalization of the 2-point retarded Green function. So this is the main claim, and then we can also generalize to the endpoint bulk correlator. So in this case, I just consider the case where the boundary fields are connected to the bulk fields by only 2 points, but we can also connect that by 3 points or 4 points and so on and so forth, and we can actually generalize this cutting rule quite easily for those kind of cases. And then our second claim is that the non-local cosmological signals are arising solely from the cut-propagators. So if we focus on the non-local cosmological signals, then actually this term and this term, you can just ignore. You can just focus on this term. And here, these cut-propagators are corresponding to the Wightman functions. So that means that you can actually factorize the time integrals on the left side and the right side, and that actually simplifies the computation. So I will explain this in the following. So this is the bottom line. And then the rest of my talk, the goal of the rest of my talk is to understand, to explain what I actually mean by, this slide. Okay, so this is the goal. Okay, so that is actually the end of the introduction. So yeah, maybe if you have questions about this introduction, you can ask me now.
Because we have mic just in front of me. I'm asking you. Somebody else who want to ask, you should come to the front.
Yeah.
Okay,
please.
So these correlators that you are considering is so in correlators is different than usual correlators in QFT.
That is right. I will actually explain the in correlators later. Yeah. Why
normally in-out correlators, and when the asymptotic states are defined in the far past and the far future in the usual case. So in this case, why you are considering in states instead of in-out?
So actually, that is the topic of the next slide. So I can maybe just explain that by using. So yeah. So this was just an introduction, and I didn't explain all the technical details. And then actually in this section too, I'm going to discuss like why we need an in correlators and so on and so forth. So
okay. Then instead, in the previous slide, you have take the kind of full amplitude 2-point function can be taken as a sum of the different diagrams with a cut.
Yeah.
Those are
clear. So yep.
Those are identical. So those are. It's not an approximation.
This is equal. Yes, right. Exact equal. And also maybe I should clarify again. So this is not a 2-point function. This could be also like a 4-point function. And as I said, so here I just draw one thick line, but this could be actually just 2 propagators, attaching here. So if you have 4 fields, so for instance, if you have the interaction that is like pi squared times sigma or something, and sigma is the massive particle and pi is the inflaton, then you can just connect 2, inflaton into 1 sigma, right? So then you can have 2 lines that is outgoing from here. So this thick line is actually corresponding to the collection of the propagators. So you can have as many fields as you want here and here. And also here, I assume that these boundary fields are connected to the bulk fields only by this point and this point, but you can also consider a case where it is connected to another point. I call it 2-point bulk correlators because this one. So this one, the bulk part is just 2-point, but this is actually like this could be 4-point correlators and so on and so forth. Yeah.
Okay. Please continue. I will ask in the later.
Yeah. So this is actually Hume's question. So the in formalism. So I want to explain why. So in this case, in the cosmological correlators case, we want to use the in formalism instead of the in-out formalism, and I want to explain why. So the cosmological correlators are evaluated at the end of the impression. This is usually taken as the tau is equal to 0. So this tau is the conformal time. And the initial conditions are fixed. So the initial conditions are usually taken as punched vacuum, but this is fixed. So in this case, this situation is different from, for instance, like asymmetric computation or in-out computation, because in-out computation, you fix the initial state and final state, right? So you want to compute like an E plus E minus going to gamma gamma. So you fix the initial state and final state, and you want to calculate the probability that this initial state is going to the final state. So that's the in-out formalism. But in this case, we don't want to, what we are interested in is not that like in-out kind of quantity. What we are interested in is like we want to just compare the correlators with the initial conditions fixed. So here in the asymmetric case, like here in this ket, you use the out state. But in this case, we actually just use the in state, like just the same state here and here. So we want to compare the correlators instead of the in-out like asymmetrics. So that makes it different from the usual asymmetrics computation. So in this case, this is called in formalism because you just take this to be in state and this to be also in state. Okay, and then so this can be expressed in this expression in this way. So this U is the time evolution operator. So you start from this zero that is defined at the infinite past, and then you evolve this state from minus infinity to zero. Zero is the end of the inflation. And then you insert those kind of operators, and then you goes back. This ket state is also the same as this plus state. So it is just the Hermitian conjugate. So that means that you just take the dagger. So which means that you go from minus infinity to zero and insert those operators, and then go back from zero to minus infinity. Okay. So the contour is given by this. So this is the this state like zero, and you start, and then you evolve. And you insert these operators. And usually in the in-out formalism, you go in this direction. But in this in-formalism case, you go in this direction. So U goes back. Okay. And
so
in this
you
case,
are interested in the correlation at the equal times. It's not instead of minus infinity plus infinity.
Yeah, that is correct. That is correct. So you just start from here and here. Yeah. And also, I think another important point is that all the fields are evaluated at this point. So this is the so-called equal time in correlators. So that's what we want to compute in the context of the cosmology. Or prime order cosmology. Yeah. And this in formalism has two types of the fields because you can pick up. So you can just express this time evolution function by the path integral, and then you pick up, for instance, the fields from this part or this one contour, and you can also pick up the fields from this two contour, the second contour. Okay, so by that choice, you actually have two types of the fields, and let's say phi 1 and phi 2. Okay. And then you can think about a propagator, so 2-point functions of these two different fields. So you have like 2 times 2 choices because the 2-point function has like 2 scalar fields. So seemingly you have 4 propagators. So if you pick up the fields from both like one contours, this G11 is just given by the usual Feynman propagator because this part is just the usual the same as the in-out formalism because you're just going in this direction. But if you pick up a scalar field from this one contour and the other scalar field from this second contour, then always the field on the second contour comes later than this fields on the first contour. So if you consider, for instance, a G21 propagator, and then this phi x should be always coming later than this phi y, because phi y is on the first contour and phi x is on the second contour. So in this case, this is just given by the Wightman function. So this is called the Wightman function, and that is given by this. So there's no, so Feynman propagator, you have this theta that is corresponding to the T product, but in this expression, there's no theta. The same is true for this G12. And if we consider like a G22, and that is given by the anti-time ordering. So this is the anti-Feynman propagator. So seemingly you have 4 propagators. And sometimes people say that this is part of the reason why the in-formalism is complicated. But what I will argue in this slide is that you can actually just change the basis of the fields to make things a bit more simple. And also, like this basis is nice because it makes the causal structure of the in-formalism more manifest. And this is really suitable for discussing our cutting rules. So I want to introduce this so-called Keldysh RA basis in the following. So we just change the basis to make the causal structure manifest. So this is just take the average and the difference of the fields. And once we check this average and difference, then the propagator of this pi r field is just given by this. So this is the average of the Wightman function, and diagrammatically we express it in this way. The important point is that there is no theta function in this expression. And if we consider the propagator of this R field and F field, that is given by this expression. So this is the retarded Green function, or retarded Green function. And so we have this data. And because this is a retarded Green function, it is very natural to assign causal flow like this. And this causal flow is actually flowing from A field to R field. And what is nice about this basis is that if we consider like 2-point function of this A fields, then that just vanishes. And you can actually show this non-perturbatory. So this is true to all orders in perturbation, for instance, or even non-perturbatory. So this basis choice reduces the number of the propagators essentially into just two, like this one and this one. And as I said, arrow is corresponding to the causal flow, and the causal flow, roughly speaking, flows from A to R field. So always R field, like causal flow is flowing into R field, and the causal flow is outgoing from A field, mainly because of this structure. And there exists odd number of the arrows that is outgoing from each vertex, because in this basis, like you can think about a partition function that is given by this in terms of path integral. But this is odd with respect to this phi one, the exchange of the phi one and phi two, which is equivalent to just changing the sign of this phi a to minus phi a. So that means that this should contain odd number of these phi a fields. So that means that odd number of the arrows must be outgoing from each vertex. So for instance, we can consider phi to the fourth interaction that is given by phi to the phi one to the fourth minus phi to the fourth, because we have going back two contours, contour one and contour two. And so if we use this basis, that is expressed in this way. And the diagrammatically that is corresponding to this one is transformed into this one and this one. Okay, so this one, so here I have three phi r fields. So this point and this point and this point, those are corresponding to the phi r fields, and this one is corresponding to the phi a fields. As I said, the causality flow, the causal flow must be flowing out, must be outgoing from this A field. So this part is A field, and then going into the phi r fields. So this part is R and R and R. You can instead have three A fields instead of the one A field, and that is given by this expression. And then, so you can in general increase the number of the A fields by two, a unit of two fields. And then if you increase it, and then you always get this additional 1/4 factor. So you can also show it generally. But anyways, this is the rule. And yet another important point is that the closed arrow actually vanishes, because once you have this kind of closed arrow, that is those are given by the retarded function. So you have this theta function. So you have the product of the theta function. So tau one. So this means that tau one should be larger than tau two, which should be larger than tau three, which should be larger than tau four. So that means that tau one should be larger than tau four, but at the same time, tau one should be smaller than tau four, which means that there's no solution. So this is equal to 0. So this is sort of the causality. If you follow the causality flow, you cannot come back to the same point.
Sorry,
so
introduction. So what is the meaning of phi one and phi two? So 1, 2 is the is that the 1 and 2 the previous slide?
Yeah, it is the same as this 1 and 2. So it is just a bookkeeping of from which contour you took this field. Because depending on which contour you took the field, you have to use different propagators. It is just because always this U dagger comes later than this U. So if you pick up the field from this one and this one, then there is no time altering. And it's just given by the Wightman function. So it's just a bookkeeping of which contour we actually chose this field.
Okay.
Yeah. If you're not used to it, maybe it looks a bit weird, but yeah, once you use it, then I think, yeah, it is just a bookkeeping in this case. Yeah. And then now I want to state, so by explaining this Keldysh basis, I believe that now we are ready to discuss the cutting rule that we discussed in our paper. But before going into our cutting rule, I want to briefly mention that there are actually also other cutting rules that exist in the literature. And then I want to briefly explain the difference. The cutting rules for the cosmological inequalities exist in the literature, but they are either one of those classifications. So there are some cutting rules that are acting not on the correlators, but also the wave function of the universe. And then people are actually discussing a lot about those kind of cutting rules. And there also exists some other literatures that are discussing cosmological, cutting rules for the cosmological collider physics, but they are actually using explicit forms of the propagators, theory details. Our point is that we actually don't have to use the theory details to show the cutting rules. And also there exists yet another paper that is showing the cutting rule by mapping the in formalism. So this specific in formalism to the in-out formalism. So you can actually map it to the usual in-out formalism in the case without any dissipation. And then there's a paper that discusses that topic. But our point is that our cutting rules are directly applicable to the correlators. And also they exist. We don't actually have to use a lot of theory details, as I will explain in the following. Yeah. And so the diagrammatically, our cutting rule is given by this kind of expression. And so from now, I want to actually briefly explain the sketch of the proof of how you show this cutting rule, because that is actually the main part of my of our paper. And so the proof consists of 3 steps. So the first, duplicate the in contours, and then show the isolated the vanishing of the isolated islands, and then the boundary between the A and B are corresponding to the cuts. But I will just explain those kind of 3 steps in the following. Okay, so we have 3 steps, and in this slide, I'm going to explain the first and second step. So the first step is, as I said, to duplicate the in contours. Okay, so we actually have this one contour, but we duplicate this contour into this kind of contour. And let's say this is A1, A2, and B1, B2. And we can distribute these fields that are sitting here, and part of it into here, at the top of this A contour, and part of it into B contour. Okay, and this is just a trick. And then actually, this contour gives us exactly the same answer as the original contour, because this A2 part and B1 part is canceling with each other, because A2 plus B1 is just given by, so first you go back from 0 to minus infinity, and you go from minus infinity to 0. So it is just given by U dagger times U. And assuming a unitary time evolution, and this is actually just equal to 1, right? So this part just shrinks, let's say. And then, once you shrink this part, it reduces to this part, this kind of contour. So it is actually equivalent to the original one, but still, it is a very useful trick to show or to prove the cutting rules to duplicate the contour. So that's why I want to do this. So this is merely a trick. Okay. And once you duplicate the contours, then you can actually show that there exists no isolated islands of the A and B interactions. So schematically, that means that, so isolated island means that, you have some A and B interaction, A interaction relations that are not connected to the external line. So for instance, this kind of diagram. Okay, so you have A interactions, and then that is connected to the B regions, let's say. And then my claim is that this is actually equal to 0. The reason why it is equal to 0 is the following. So first of all, the propagators that are connecting to this B max of A, which let's say has the largest time argument, inside that islands are independent of the 1 and 2 indices. This is just because, so let's say that in that region, you have the vertex that is living here and here and here and here and here and here. So these are corresponding to the Vmax of A1 and 2. But then, so the propagators, a time ordering between those kind of fields and this field is independent of whether this VA max is sitting here or here. Or in other words, so this part of the contour, you can actually just shrink because there's no fields here. And that is equivalent to this one. Then there's no distinction between this VA1 and VA2. That means that, this one, so these propagators are equal to these propagators. So that is the first step. And then the second step is, so second argument is that the propagators connecting this VA max to outside. So let's say this is the VA max. then the propagator that is connecting from this BMX to this B field, this part, is also independent of these 1 and 2 indices because B fields always appear later than A fields in this contour. So it is always just a Wightman function. So all the propagators that are connected to this BMX is independent of the 1 and 2 indices, but the vertex itself, the interaction itself, actually has this plus minus, and that is coming from the sign in front of this S phi1 and phi2. So that is just given by the fact that you are evolving in the opposite direction. So this direction and this direction. Then they cancel with each other. So this means that if you have this kind of Bmax or islands of these A interactions, that must be connected to the boundary fields because otherwise it just vanishes. And so this is a bit technical, but if you know, for instance, the Boltzmann's lifetime equation as a proof of the Keldysh rule, actually also there, you can find a very similar argument. So maybe you don't have to understand all the technical details, but the point is that if you have some region that is isolated from the outside, then that vanishes. Okay, so that is the second step. So the summary of the step 1 and 2 is, the following. So the step 1 and 2 tell us that the internal A and B interaction region should be connected to the external A and B fields. And that means that each diagram must have a boundary of this A and B interaction regions, and this boundary is corresponding to the cut. So this is the bottom line. Okay. And this ordering of the A and B fields are independent of this 1 and 2 fields again, because always the B contour comes later than A contour. So that means the propagators in between this boundary is corresponding to the Wightman function without any time ordering theta function. And also the fields that are consumed as this Wightman function is independent of this 1 and 2 indices. So that means that those fields are R fields. So that means that, so as I said, time arrow should be flowing into this R fields. So the time arrow should be flowing into the vertex. So in the end, the bottom line is the following. So if you consider this kind of diagram, and then you can just assign this as an A field and this as a B field, okay? Then what I said in this step 1, 2, 3 is that there must be a boundary of these, B interactions and A interactions. So if you have the boundary here, and then, this is corresponding to the cut, and this is corresponding to the cut, and this is corresponding to the cut. In this case, all the interactions inside this block is coming from this B region. In this case, it is coming from the A region. In this case, this part is coming from the A region. This part is coming from B region, and there's a boundary in between. And this is the Wightman function. But we can symmetrize the A and B assignments to the external fields, and then that gives us the desired result. Okay, so this is the sort of the sketch of the proof of the cutting rule. So the bottom line is that you can just think about dividing these diagrams into A region and B region. And then the previous argument tells us that there must be always a boundary in between. And then the boundary gives the cut-propagators. So I think, also in practice, if we want to think about how we can cut the diagrams, then we can just think about how we can assign these A regions and B regions. So also in practice, it's kind of, useful to remember this kind of argument. So this was the proof, and then we can actually generalize this to the endpoint bulk correlators. So in the previous case, I just considered the case where the boundary fields are connected to the bulk fields only by 2 points, but we can also think about 3-point bulk correlators like this, and then cutting rule is given by this. And again, in this case, we can show this kind of relation by further duplicating contours. So instead of having just A and B fields, we can actually consider A and B and C fields. And again, we can just think about how to assign A and B and C regions, and then get this kind of cutting. So those are just examples. So for instance, melon diagrams case, we have the cut here, and cut here. So in this case, we have let's say this is A field, and this is B and B and B. And this is A and A and B. And this is A and B and B. So depending on those kind of assignments, we can have 3 different cuts. And also 2 loop diagrams are given by this, and 1 loop 3-point diagrams are given by this. And one can actually also brute forcefully show those kind of cutting rules, but the calculations are more and more tedious for the complicated diagrams. So I think, So even though, as I said, like this, duplicate and control is just a trick, and you don't have to do that. But if you do that, then you can nicely show those kind of relations without any additional complications. So in our paper, actually, we also forcefully show those kind of cutting rules, not by duplicating contours, but that was really messy. So I think it is a nice idea to actually duplicate the contours. So that is actually the end of this section 2. Maybe it was a bit technical, but hopefully I can just bring you. I could just bring you the main idea. So if you have any questions about this section 2 about the cutting rule, then maybe you can ask.
So maybe there are some students in the audience. So would you mind reminding us of what is this Kotkowski rule in standard QRT? So what is the implication of this cutting in the Feynman diagrams?
So what is the implication?
Would you mind?
Is that the question?
Would you mind reminding us what is the implication of cutting the Feynman diagrams?
So for the in correlator case, I will actually discuss one implication of those cutting rules. So is it more about a question about the usual?
The previous like a 2-point correlation function.
Yes.
There are 3 cuts you can make. 2-point function.
Yeah, 2-point function.
The
cut is given by this one, this one, and this one.
Three ways of cutting.
Yes.
Feynman diagrams. And you said the last one only contribute to the particle production. So this one, only this one contributes to the non-local cosmological correlator signals. Yeah. And actually, there's a complication about the local cosmological correlator signals that are also coming from the particle production. And then, so in our paper, we didn't fully understand the property of it. So in this talk, I'm actually gonna focus only on the non-local cosmological correlator signal. So this is part of a particle production. So that is coming from the particle production, but this is not the full particle production correlation. There are some other particle production correlations. So for instance, let me take the one loop correction and fight to the fourth theory in QRT. One loop correction, you can cut one of the internal propagator, or you could cut both of them to make them loop particles to be onshore. You can take the loop particles to be onshore, then the one loop correction to the 4-point function becomes, this optical theorem, the amplitude square for the onshore particle production. So that is connected to the particle production, right? The by cutting means take the imaginary part of the one loop amplitude. Then in this case, you are doing the similar thing. Yeah. So actually, this cut, as I said, is the average of the Wightman function. But taking the average of the Wightman function is equivalent to taking, I forgot actually the real part or imaginary part. Depends on how you assign I. But taking actually the imaginary part, let's say, of the Wightman function. So in that sense, this is really corresponding to the usual, also the Feynman dynamics is we take an imaginary part and we just cut, and cut is corresponding to taking an imaginary pattern, which is corresponding to putting the particles on shell, right? So it's quite similar. Yes, it's quite similar. Yes. Okay. So for instance, as you said, if you have a 4-point interaction, then so this melon is just bounded, right? And then you can cut here and here and here. So as compared to the standard QRT calculations, so I see that this black solid line and the left diagram, we have a melon diagram. Attach it to a thick black line. Those are supposed to be external propagators. That is correct. Yes. Those external states. Yeah. And then the melon, those are loop particles. Yeah, that is correct. Yes. Then why are you making a cut to the external propagators? So
I think here it is slightly different from the asymmetrics because asymmetric case you consider amputated diagonals, right? So you use the LSD reduction formula. So you have the correlators, but you actually kind of strip out the external propagators, right? So that's what you consider. Here you actually also have this propagator that is remaining because we are not considering the asymmetrics, we are actually considering the correlators itself. In that case, you actually have to also include this cutting of the boundary, bulk to boundary. So that is maybe that is one difference between the asymmetrics and those correlator computations.
Okay, that sounds good. Okay, thank you.
Okay. So are there any further questions? Yeah, slightly more because this is a bit technical, but
These diagrams have both the real and imaginary part. What would happen with the real part?
Yeah, you can come close.
So like these diagrams in general should have both the real and imaginary part. And with the cutting, you are just taking the imaginary part. What would happen with the real part?
So here on the left-hand side, I'm actually not taking any imaginary part or real part.
Exactly. So that contains basically both the real and imaginary. Because I know in the context of vectogenesis, that gives us the imaginary part. And there we can use the cutting rule by putting the internal particles on cell. But here we don't have anything like that. So it should have both real and imaginary part.
So we don't. So this is just an equal. And here, actually, I'm not taking real part and imaginary part. But maybe my answer to your question is like this quantity itself is just corresponding to the curvature perturbations, like correlators of curvature perturbations. So actually, it is sort of real to begin with.
It is real from the beginning.
Yeah, I mean, you do the moment transformations, like a Fourier transformers also. First of all, I'm not completely sure whether this quantity itself is real, but it is related to some real quantity, right? In the end, that might be my answer to your question.
I think I understand the part that for the on-cell production of the particle, like the cosmological correlator, you are taking the imaginary part, and that's how you make the cut and you have the particle. But I was trying to understand if the real part has also some contribution, no problem.
So are you talking about the real part of this intermediate particles or what?
Yeah, exactly. The real part of that diagram.
For instance, like on this part, I'm actually thinking, so let's say this is the imaginary part. And this part, as I said, actually I have the definite flow of the time, and that is corresponding to the real part of these particles. So here I'm taking the imaginary part of this propagator and real part of this propagator. So I'm just combining these two, these stuffs.
I see. They are all imaginary.
Yeah.
They are all imaginary, but you are distinguishing between local and non-local contribution.
Yeah, exactly. So I don't know whether this is a very precise template, but roughly speaking, let's say that you want to compute some, I don't know whether this is real or imaginary, but let's say imaginary quantity or something, and then you take the imaginary part here and the real part here and here, or you take the imaginary part here and the real part here and here, and you take the imaginary part here and real part here and here. Roughly speaking. I think probably it's not that exact, but you're doing that. So that contribution is coming from this diagram instead of this diagram. Hoping that answers your question.
I see. Okay.
Okay. So if there is no further questions, then I will proceed to the application of this cutting rule. So this is one implication. I feel like there could be like many other implications, and actually that's what I want to explore after things are settling down. And then I was just moving, so I didn't have enough time to think about it. But actually, what kind of implications you can get from this cutting rule is sort of the future direction that I want to pursue. But here in this section 3, I will discuss one possible application of this cutting rule, that is the non-local cosmological collider signals. Okay, so before discussing the cutting rule for the non-local cosmological collider signals, I want to briefly mention one property of the so-called fully intelligent function. So the cutting rule, as I said, is decomposing the diagram into this one and this one and this one, right? And here the important point is that you have this definite direction of the causal flow. So you have this arrow here. also this one, you have the arrow here and here. And this function is called a Fourier retarded function. And then, so this Fourier retarded function is really the fundamental building block of the cosmological correlators, in the context of our cutting rule. And that is given by this kind of function. And then you can just strip out these external propagators. And then, this is the correlators of the operators. Okay, and then that is given, that is defined as this P, R, A, and that is called the Fourier retarded function. And this is a generalization of the two-point retarded Green function. And actually, it satisfies some microcausality relations. So the Fourier retarded function satisfies this kind of relation. So it vanishes if any of these, y indices that are the indices of this, OA operators. So if any of those, points are outside of the right cone of this X, then it vanishes. So this is kind of the microcausality relation of the Fourier retarded function. For instance, for the two-point function case, you can just think about this VRA, and then that is just given by this retarded function of these operators O and O. So a microcausality directly tells us that if this X and Y are outside of the right cone, then this just vanishes. And then you can actually generalize it to the endpoint functions by the mathematical induction. So this is just given by the nested commutator of those kind of operators, and then you can in general show that it satisfies the microcausality relation. So this is one property that the Fourier retarded function satisfies. So as I said, the non-local cosmological collider signals are arising from non-analytic dependence on the spatial momentum. But the microcausality tells us that the Fourier retarded function has a finite support with respect to the spatial argument. So this is just rephrasing what I said in the previous slide. So if any of those y points are outside of the right cone, so if the spatial component is larger than the time component, then it vanishes. So this means that if you fix this conformal time like x0 and yi0, then this has only a finite support. This is non-zero only for finite region of this x vector minus y vector. So if your function has a finite support, then its Fourier transform is analytic in with respect to the variable that you use for the Fourier transform. So its Fourier transform is analytic in the spatial momentum, and then this is guaranteed by some mathematical theorem. So this in practice means that this Fourier retarded function is analytic in the spatial momentum. So the non-local cosmological collider signals are non-analytic dependence on the spatial momentum. So this fact tells us that therefore the non-local cosmological collider signals are arising solely from the cut-propagators. So it should be coming from the cut-propagators. And in general, bulk to boundary propagators are not having any cosmological collider signals because it doesn't contain any mass information of the heavy particle. So that means that if we focus only on the non-local cosmological collider signals, then we can just focus on this last diagram where the cut is in between this bulk part. And as I said, the cut is corresponding to Wightman function. So these time integrals are factorized. There is no theta function. So the time integrals are factorized, and that actually simplifies the calculations in certain cases. So you can actually perform the integration of this part and this part separately. So you kind of reduce the number of the time integrals by a factor 2. So that I think is good, especially if you're considering some complicated diagrams. So that is the cutting rule for the non-local cosmological collider signals. Okay, so up to now is the general argument, and then in the following, in the remaining 5-10 minutes, I will discuss some explicit computation, because so far I just discussed the general argument. I didn't discuss anything about the actual computation. So I want to show some a simplest example on how the computation works. Also, I think maybe by this example, even if you haven't seen any computation of the cosmological correlators and cosmological collider signals, maybe you can just get a flavor of why the computation is really complicated. Okay, so I will discuss the two-level single exchange diagram with this Lagrangian. So let's say that this phi. So this actually has the conformal time integral. So phi prime squared times sigma. So sigma is the heavy particle, and this phi is the inflaton, let's say. So the massless propagator. So inflaton is close to the massless. So I just ignore all the slow parameters. So the propagator between this phi field is given by the massless propagator that is given by this. And this is relatively simple. But if you have this kind of massive particle, the massive propagator is given by this expression. So here H is the Hankel function. This is a special function of the first kind and second kind. This nu is given by this expression. Okay. So you see that there's a Hankel function. So it's kind of complicated. But one important point is that if we take the retarded Green function or equivalent to the propagator between this R field and A field of this sigma, and that is given by this expression. And so this J is the Bessel function. So Hankel function is related to the Bessel function. But the important point is that it is analytic in the momentum, special momentum K. It is just because J nu, the Bessel function in general satisfies this kind of monodromy relation. So if you change the argument by 2 pi phase, then you will get this 2 pi nu phase. But here you have nu and minus nu. So if you rotate this k and this k at the same time, they cancel with each other, which means that this is analytic in k. So this is just one example of our general argument that the Fourier retarded function is analytic in momentum. And what I have to do is that I have to compute the H-channel process. So we can just focus on the H-channel process and we can just think about the diagrams. So this 4-point function is given by the diagram, this one, this one, this one. And as I said, you can just cut here, you can just cut here, you can just cut here. And then direction of the time is given by this. So this interaction, as I said, you have to have one outgoing arrow at least. So it is the direction of the arrow is kind of fixed like this and this and this. And for instance, if we consider this one, this is given by this kind of expression. Okay. The important point is that here, because I have this theta function, the time order in theta, so integration, so this tau L is corresponding to the time on this left-hand side, and then this tau R is corresponding to the time on this right-hand side. So you have to perform the integration, as I said. And then you actually have this tau L here, because this is the retarded Green function contains the theta. So what I have to do in this computation is that you have to actually compute this Hankel function or Bessel function, the time integration of this Bessel function. And actually you have to do it twice because they are nested. And you kind of get an idea why this kind of computation is in fact is complicated, because you have to do the time integration of the special functions. So you have to understand what you get after integrating the special functions. But what I said in the previous argument is that if we focus only on the non-local cosmological signals, then we can actually ignore this kind of diagram. And we can just focus on this diagram with the cut on the bar, so bar cut diagram. And it has a factorized time integral. So this is given by this kind of expression. And this GRR doesn't contain any theta. So there's no a tau L or something here. And this GRR is just given by the product of the Bessel functions. So still you have to perform the integration of the Bessel function, but you have to do it only once, not twice, which kind of simplifies the life. So the factorized time integrals simplifies the calculation. In particular, we can actually compute the non-local cosmological correlator signals of this diagram, and that is given by this. So still you have to, as I said, perform the integration of this Bessel function, and that will give you actually the hypergeometric function. So it looks still kind of scary, but the computation is a lot easier compared to the other diagrams. And here, this has a non-analytic dependence on this vector sum of the momentum. So this nu. So this nu is given by, as I said, 9/4 minus m squared divided by h squared. So this is actually non-analytic dependence on this momentum. So this is really coming from non-local cosmological signals. And for instance, we can also expand it to the loops, and then in our paper, we also computed this kind of diagram. But so this is the sort of the simplest example of the cosmological correlator computations, and in particular the application of our cutting rules. Okay. So this is sort of actually the end of my talk. So I want to summarize my talk. So first of all, I argue that there exists a general cutting rule for the equal time in correlators, and that is given by cutting here and here and here. And then this arrow is again corresponding to the the direction of the causal flow. And then so this function is what is called a Fourier retarded function. Okay. And the is corresponding to the cut, and that is the average of the Wightman functions. And in particular, as an application of this cutting rule, we argue that non-local cosmological collider signals are arising only from the cut-propagators, because all the Fourier functions are analytic with respect to the spatial momentum. So it should be coming only from this diagram. And that actually factorizes the time integral. So in certain cases, like that actually simplifies the computations a lot. So this is the summary. And then, so this is actually the same slide as I showed at the beginning or at the end of the introduction, but hopefully now you have a better understanding of what I'm saying in this slide. And also, I feel like there can be other future applications of these cutting rules. So in our paper, we applied it to the non-local cosmological collider signals, but I'm very interested in applying it to some other directions. So I think maybe the easiest one is applying this to some models of the cosmological collider physics that has some chemical potentials. Because if you have the chemical potentials, you can actually enhance the cosmological collider signals. And then what is nice about a cutting rule about our cutting rule is that it doesn't depend on theory details. So even if you have the chemical potentials, you can just apply it. So maybe you can apply it to the models with the chemical potentials. That is one easy application. In my talk, I focus only on the non-local cosmological collider signals, but actually, as I said, there exists another type of the cosmological collider signals that are also coming from particle production. That is so-called the local cosmological collider signals. And so understanding those local cosmological collider signals, and also the backgrounds or the high-dimensional operator contributions are also important. So I also want to have a better understanding about those kind of signals in the context of our cutting rule. Also, I think yet another interesting thing is we can also compare our cutting rule with the cutting rules existing in the literature, especially there, as I said, there are some cutting rules that are applying not to the in correlators, but to the wave function of the inverse. But of course, they encode the same amount of the information, I believe. So, it's kind of interesting to compare how they are related to each other. And the last thing, and then I'm very interested in actually this topic. The last thing that I'm thinking nowadays is what is the analytic property, analytic structure of the Fourier functions? So as I say, the Fourier functions are the fundamental building blocks of the cosmological correlators in the context of our cutting rule. So if you understand the analytic structures of the Fourier functions, then maybe you can actually compute the Fourier functions by using that structure. So, for instance, if you understand the analytical structure of it, maybe you can utilize that to write down some differential equations and solve it and so forth. And then maybe we can sort of bootstrap the computation of the cosmological correlator. So I don't know. So this direction I think is really interesting. So those are the future directions that I'm thinking about. Yeah. Okay. I think that's all what I want to say. So I stop here. Thank you.
Okay. I think there is no howling. I changed the speaker to mine.
Great.
So I think everybody can feel free to ask any questions. Maybe I hope that the microphone in my computer is working well. To speak out and.
In your case, you have considered the in formalism. So same kind of conclusion can be done with the in-out, like the standard QFT, if we use that kind of thing, or standard QFT is not applicable here. Right.
So I think so. In your formalism case, people already discussed the cutting rules a lot, right? Cut-off rule. And for instance, so I mean, the answer is yes, but at the same time, I think things are very well known in the context of in-out formalism. But maybe I can say one thing. So here I duplicated the in controls, right, for the proof. And then, as I said here, also in the in-out formalism, people actually do very similar stuff. So people sometimes, so I think maybe it started from Wightman, but Wightman, for instance, introduces stackled interactions on top of the usual interactions, and that is kind of equivalent to. So you usually have. So in other formalism, you usually have just a contour that is going from left to right. That's it, right? But you can actually add another contour that is going back, and that is corresponding to taking the complex conjugate or Hermitian conjugate of the initial contour. So you can add such kind of stuff, and you can discuss the bodies interactions coming from this other contour. And then, by doing a very similar argument, you can actually show that you have the boundary between this, original interaction and the added interaction, like a circular interaction, and that boundary is given, boundary is corresponding to the cut. So in that sense, yes, you can use a very similar argument to the in-out formalism, but at the same time, I think things are very well known in terms of the in-out formalism. So also, I feel like this cutting rule is well known. So the cutting rules for the in correlators are also well known in the concept of the thermal field theory. But my impression is that it's not that well known in the concept of the cosmological correlators. So that's I wanted to draw the attention of the community to this cutting rule. Hopefully that answers to the question.
So I understand actually in formalism is required because we have correlation at equal times. We are not interested in the correlation at different times, like a scattering.
That's right.
The scattering amplitude matrix. So maybe so kind of propagation of the correlation at present, right? We want to understand the correlations at present and how those variables evolve. This is interesting, right?
But how correlation will exist at the same time in two different positions? It's a violation of causality.
Because they were in the sub-horizon, right? These perturbations once in the horizon during inflation, right? And can you ask the question?
Yeah, in general, like the 2-point correlation function, we always need the non-local. Because of the conservation of the causality, we have to have two different points and two different time. But here you are saying that in the in correlation, it has to be in the same time. But if they are in the different position, how they can be correlated?
I mean, they could be interacting in the past, right? So that's what is happening here.
Yeah, so they are interacting within the horizon during inflation. So they are causally connected.
Okay, in the early time, and now the inflation happened, and
so for instance, this diagram, this is corresponding to the future, a future surface, right? So this is the corresponding to the end of the impression. But actually, things are happening in the bulk, which was in the past, and that is propagating into this direction. So that is what is happening. And also, maybe I can also say another thing. So as I said, the cutting rules are known also in the context of the thermal field theories, but in that case, actually, in some sense, the things are more complicated because in that case, people also want to consider different time correlates, not just the equal time correlators, but the correlation function between different time points. And here, what is nice about the cosmological correlators is that we are interested only in the boundary fields. So that actually simplifies the cutting rule. So so if you discuss cutting rules for the non-equal time in correlators, then things are a bit more complicated than this kind of cutting rule. So that is actually simplifying the argument of the cutting rule. Yes, that is actually right.
So when you actually talked about microcausality at some point, right? This is also kind of imposing causality condition for the space-like separation.
Yep.
And those separation is not is different than the correlation that we are interested in, right? So we want some correlation, but here. What do you mean by this microcausality imposed on that function?
So first of all, I think so. Maybe first of all I should clarify. So this XL is corresponding to the conformal time. So I'm imposing the microcausality relation on the conformal coordinates. So that's what I'm doing. And then here my argument is I input the microcausality to argue that the cosmological correlator signals are arising only from this. But so this function satisfies the microcausality. But for instance, maybe better to have this one. So this part actually satisfies so this part actually vanishes as of the light cone because of the microcausality. But microcausality doesn't restrict the behavior of this function because this is not given by the commutators.
I see.
So the non-local cosmological collider signals are arising from this one that is not restricted by the microcausality.
I see. Okay. I see.
So microcausality sort of restricts from where you can actually get a non-analytic dependence on the momentum because some parts of the diagrams are given by just nested commutators and then that vanishes as a direct cone, but not all of them.
Okay. So maybe you can ask some more questions. Do you have any questions?
No.
So maybe you can ask some general question. Also. So here maybe I can ask maybe while you are thinking of questions. So this cosmological collider signals, you talk about correlations in a general way, and how is it related to observables? Our correlation function is related to observables, and these observables that you are talking about in Platon is specific, right? Correlation between the Platon perturbation.
So, for instance, one signal is that. So this is eventually just the correlation function of the influence on fluctuations, and that is related to the correlation function of the curvature perturbation. So this is sort of non-causality of the curvature perturbations. What you can do, for instance, is that this nu, if the mass is sort of larger, like a mass, so maybe I should just show, nu is given by this. So let's say that m is large, so that this is imaginary. Then this nu is kind of imaginary, I times m divided by h. So this is actually an oscillatory function. So what people usually discuss is that people usually take the so-called squeeze limit. So this case, this is a 4-point function, but you can also think about a 3-point function. And a 3-point function has 3 momentum, of course, but you can take one spatial momentum to be much small compared to the other 2 momentum. So that is called a squeeze limit because in the momentum space, you're kind of squeezing the triangle. So this function tells us that in that limit, you actually have oscillatory features as a function of the ratio of this small momentum divided by the large momentum. So in practice, what I can do is you can just consider that kind of compression and just plot the non-causality and then see if there is some oscillatory feature. That's, for instance, one observable. And I think this year some groups are trying to doing some data analysis of the CMB and also the landscape structure to try to look for those kind of oscillatory features. So in practice, that is going to be one kind of observable. In general, what you want to do is you want to look for some non-causality that are non-analytic with respect to the momentum. So that's what I want to do. Of course, oscillatory feature is one example of the non-analyticity.
So in this example, you took the 4-point correlation function, but by spectrum, we need to take the 3-point correlation function, right?
We can also consider a 4-point function. We can also do that. I think observationally, probably it is easier to consider a 3-point function. So but we can also do for the 4-point function. I just said 3-point function because usually observationally, people discuss the 3-point function.
For 3-point function, the diagram structure is different than you have drawn in the slide.
So actually, it could be the same, but there's one complication that is arising for the 3-point function. Maybe I should also clarify that. Because the reason why I consider the 4-point function is that in the 4-point function case, there's a clear distinction between the non-local cosmological collider signals and local cosmological collider signals. Maybe I should just go back to the definition of them. So this is the definition, right? And then 4-point function case, you can put 2 fields here, 2 fields here. And then this case is going to be different from this KL and KR. But if you consider 3-point function, you can put two fields here, but you should put only one field here, right?
Mm-hmm.
The vector sum and the scalar sum is going to be the same. So let's say that you have only one field on the right-hand side, then this KR is going to be equal to KS. So in that case, there is no distinction between this local signal and non-local signal, right?
Mm-hmm.
Yes. So that means that in that case, you have to consider both the local signal and non-local signals at the same time. And as I said, I have a better understanding of the non-local cosmological correlator signals, and then compared to the understanding of the non-local cosmological correlator signals, like our understanding of the local cosmological correlator signals in the context of our cutting rule is still a bit limited. So that's actually one thing that I want to understand better. But if we consider the 3-point function, we have to consider both. So that's why I wanted to separate these two. So that's why I consider the 4-point function. But this is more like the problem about my understanding or our understanding about our cutting rule and the implication to the local cosmological correlator signal. So observation, there's no problem of taking the 3-point function.
Mm-hmm.
So that's the reason why I consider the 4-point function.
Okay. So, question? So actually, thank you for your nice talk today. And I know that you also worked on Higgs R-square inflation for cosmological.
Yes.
So
I also worked on that.
There's some connection to your general formalism, right?
I mean, I kind of entered to this cosmological collider community through that paper, and then the computations were quite complicated, actually. And then, I was just thinking about is there any way of simplifying the computations? Yes. So those are connected.
Okay, I see. So I hope that we can see next time in person. And
hopefully.
You should come to CAU,
exactly.
And chat more actively and more efficiently. Yeah. Okay. Okay. If there's no, you have a question?
No.
Okay. Thank you. I'll see you next time.
So
Okay, bye.
Yeah, see you. Bye.
Okay, bye. See you.